everyday life, in our everyday life. If we need to take a very crisp look into what is exactly meant by machine learning, then first of all, there are two words, machine and learning. Machine essentially stands for a computer with one Neumann architecture, the classical computer, not the quantum one till date. And learning, if you leave out all the philosophies associated with the word, then a learning system is a system which can take the appropriate future decision based on past experiences. And with more experiences flowing in, this capability of taking the future decision also improves. Okay, so this particular picture gives a quite direct relation and distinction between traditional programming and machine learning. You have a computer. In case of traditional programming, you provide some data, which might be some unsorted lists of integers, into your computer as input, and a clear program. What is a program? It's a sequential set of instructions, which this computer will execute almost like a clerk. Okay, it doesn't apply anything of its own. Just like a clerk, the computer will execute these instructions one after another and provide you. This program may be the implementation of a bubble sort algorithm, and the computer will provide you a sorted list of integers. This is traditional programming. What is machine learning then? In this case, the computer will be shown with some input data, like some sorted lists, unsorted lists of integers, and the corresponding output example, what we want to do with this data. So these are the corresponding sorted lists of integers. And then we expect the computer to learn how to sort these lists of integers. And in machine learning, the ultimate dream goal is let the computer write down the sorting program. Let the computer figure out the correct sequence of steps following which it will produce a output, a desired output from the raw input data based on the example outputs which it has been shown earlier. This is the dream goal. Coming to supervised machine learning framework, supervision means there is a teacher, there is a human expert who will be providing some guideline to the machine. This is much like when we start learning at a very young age, and all of us, all of you must have gone through this experience. When I was a kid, my mother used to point to some, pictures from the kids' book and say, this is a cat, this is a dog, this is a rat. After some rounds of such training, one day when I go on road with my mother, and a little creature passes by me waggling its tail, then I would yell out, "Mom, look, that's a dog." I was pretty excited. So what did I do? I took a decision about the category of that creature based on the experience given to me by my mother as she was pointing out to those pictures and she was telling some names to me. So somehow I could match that name with the gross shape, texture, appearance of that creature that I actually saw on road. So this is supervised machine learning framework. And this entire framework could be, summarized by using this equation y is equal to f of x, simplest mathematical equation. Y is the output or outcome. This x is basically an abstract representation of a real life object, which we call a piece of data. Everything around us, which we could abstractly represent to a computer in terms of certain numbers sitting together, finally in terms of bits and bytes, qualify as a piece of data. You go to a bank, apply for a loan, in your name one file opens up in the bank. So you start to be specified in terms of your CIBIL score, your fixed deposit amount, and blah blah stuff. You become one piece of data. All of us are kind of piece of data to the governance under which we come. So y is equal to f of x. X is such an abstract representation of a data item. F, function is much like a factory. So x is like the raw material going into that factory. F is that factory, that model, that machine learning system, and which finally gives out y. What is y? Y is the decision, the prediction, the inference about the category of x. Okay, And this inference, this model f of x is built based on an initial set of labeled examples for which the inferences are already done or carried out by some human expert. Based on such inferences, so finally some kind of criteria function is minimized and the training happens. Similarly, and once this function is made, when a new example comes before the machine, it should tell us the actual predicted value. This is just a comics illustration to just to tell you what is happening. So the features of an image can go into this particular function, and the function can identify the central object of the image or take a decision about the category of that central object. Nowadays, so machine learning is to always find the appropriate functional representation which maps from a given input space to some kind of output space. The inputs may be the abstract representation of data items at your disposal, and the outputs may be the categories or classes to which they should belong. In case of regression, now different machine learning tasks come under the same framework. For example, regression, in that case, the output y could be a continuous scalar number. Regression is the situation when we try to find out a functional relation between a set of independent variables and some dependent variables. Okay? Like, for example, the death rate due to cancer, how does it depend on average age, smoking habits, number of years into smoking, number of years into obesity, and so on. So these factors and the death rate, annual death rate due to cancer, say in India, how they are related. We need to find a function of the same form y equal to f of x. Classification, in case of classification, we want to put the output y as a discrete number. So the output is a class. If you have three classes, you will have three outputs, and these three outputs may be shown. This is one way to show them, is to use the one hot vector encoding of the output for the three classes 1 0 0 0 1 0 and so on. Structured learning or prediction, this is the most important part where we are going. In that case, the output is a sequence, a matrix, a graph, or a tree. The output is always, this is the most important part where modern machine learning comes, because nowadays the data is not merely composed of a vector of some features. Earlier what we said, okay, we have a iris flower. Now the iris flower is a real object, it's like a rose flower. But the computer doesn't understand its fragrance or color or appearance. The computer understands only numbers. So what we do, we take four measurements of the iris flower: the sepal length, sepal width, and these four numbers sitting together start specifying the iris flower. Geometrically, those who are aware of mathematics, the flower, which is a real physical object, maps into a point in a four-dimensional geometric space. Okay, we call it a feature space. But nowadays, the data has become way more complicated. Now, every Facebook profile is a data item which could identify a user. So that Facebook profile contains image, text, video clips. It's a multimedia data, heterogeneous, and it is growing every day. You are posting a lot of pictures almost every week. So now if I want to draw some inference by analyzing the Facebook profile of different people, maybe this is a very common practice to draw the inference about the political opinion of that person, to which party that person is likely to cast a vote. You gather profiles of different people from different regions, and IT cells of many parties regularly do this job. So in these situations, specifically we talk about structured learning or prediction. In that case, X and Y may be very, very, very complicated data items. X could be a sequence, Y could also be a sequence. X could be sentence in one language, Y could be, this is typical in machine translation, Y could be the corresponding translated sentence. X could be a speech signal. Speech recognition systems, all automatic, this what you call subtitling systems. Nowadays, you could subtitle your video clip by using a simple web-based tool. So the subtitling system, they take X as the speech and Y could be the transcription in some language. Chatbot X is a sentence that perhaps the user types and Y is a defeating response from the machine. Not only that, X and Y could also be matrices. X could be an image like this. And so you make some rough sketch of some building like structure, and Y is just a camera clicked, as if it is a camera clicked, but artificial image of such a building. Okay, this image is actually composed by the machine. It is not clicked by any camera, and it matches. This is called conditional generation. This is where we are going actually. So nowadays you can have your machine come up with an image like this, which will be conditioned by this distribution of the windows. This the European houses have this sort of nice balconies which are full of colored flowers and so on. Similarly, this could be your input and this could be your output. You could do colorization. So from black and white to color. Then you can change the color conditioning also. Make all bottles green. Input could be a text of line of text like this white and yellow flower have thin white petals and a round yellow stamen. And Y could be something like this. Y could be this sort of befitting picture which matches with your caption. Now coming to this, why is it so hard? If your input is a motorcycle, every human being knows, okay, well, as soon as you look at this picture, you immediately capture some very important abstract and higher level features. By the way, so you immediately, I'm coming to this, you immediately see it has engine pipes, it has handles, it has wheels, so it must be a motorcycle. But the machine, the camera, sees only piles of numbers, which are encoded forms of brightness of different points from the image. So if you take this much small a portion from this image, it actually unfolds into piles of numbers, which you could see here. So these numbers or the pixel intensities, they are called the lowest level features because they are very close to the computer but very far from human heart, human mind, human interpretation. So they are like what? They are like the machine language code that actually comes finally is prepared as you compile a high level language code. Like you compile a .c file and a .exe file is created. That .exe file, human beings are unable to interpret or go through because those are written in platform dependent machine language code. Similar are these pixel level features. So somehow we need a way to compile the pixel level features. Suppose that in such a way, we need to combine the pixel level features in such a way that we get to very high level abstract higher level features from which. So what are abstract and higher level features? When you look into the face of your friend from a Facebook post, you don't say, okay, the top left corner pixel is 128, beside that 137, beside that 228. No, you immediately recognize some abstract and higher level features. Like there is a cut mark on the chin, there is a mole on one left cheek, there is the nice mustache, thick beard, this sort of things you identify, right? So suppose I mount a camera on the doorway of my garage and I want to demarcate between cars versus non-cars. I don't want an elephant to walk into my garage. In Kerala, that regularly happens. So I mount a camera on my garage and whatever picture it captures, I represent the picture in terms of two such arbitrarily chosen pixels. So every picture boils down to a point in this two-dimensional space. One along x-axis, we are plotting the values of pixel 1, and along y-axis, we are plotting the values of pixel 2. Now, these two pixels are completely decorrelated. So if I try to plot them in this way, what we end up is called a khichdi in Indian language. It's a complete mixture, khichdi. So from this mixture, cars and non-cars, they will have no correlation between these two pixels, and it will not be possible to separate these two classes by a simpler classifier. Instead of that, suppose I have a picture of this sort, and I take two 3 cross 3 or 5 cross 5 matrices fitted with very intelligently learned or tuned coefficients. Now I drag these two matrices over the image by using two nested for loops, either 3 cross 3 or 5 cross 5. One of these matrices is endowed with such coefficients that as soon as it captures a handle-like shape or a wheel-like shape, it provides a very high response, close to 10. If it cannot find a handle or wheel-like shape, it will provide almost zero response. So I drag these two submatrices over the image and note down their average response. Of course, what will happen? Now my one axis is plotting the response of the handle detector and the other axis is plotting the response of the wheel detector. If I could have such two matrices, what would happen? For the car, all car images will have handles, wheels, etc. So they will accumulate far away from the origin. For them, both the detectors will record a high response, and for non-cars, they will record a very low response, accumulating those points close to the origin. And then even a very simple linear classifier, a perceptron, a very simple logistic regressor would be able to demarcate between these two classes. So a lot of it depends on how you represent the most important higher level abstract features from an image. And this is exactly what this sort of feature detectors are trained in convolutional neural networks. This is exactly where deep learning comes into play. And nowadays it's not very easy. And if you look at this sort of human brain is remarkably fast at it. So if you look at this data set, it's a data set. It contains 8 images from 2 classes, total 16 images. Classes are sheepdog or mob. If you look at this set of pictures for about 5 seconds, you perfectly know what is what. You can tell me what is sheepdog or what is a mob. But to make a neural network or a machine learning system identify the same thing is not easy. Puppy or baggy. You can tell immediately which one is a dog puppy and which one is a bagel, barn owl or apple. Not only that, you can tell me as a human being. Obviously, if you are good enough, if you are not drunk, you can you can also tell me based on what abstract and higher level features you are drawing your conclusions. For example, in this case, you will tell, okay, there is a huge distance between the two eyes of the owl, but the seeds of the apple are very close to each other. Okay? Similarly, this is a very, very difficult data set. Chihuahua or muffin, you can see there are multiple cakes, there are multiple dog puppies, but still you can tell me based on what features you are distinguishing. Probably you will tell, okay, the eyes and nose of the dog puppy are arranged on the vertices of a regular triangle, but the cherries on the cake are much haphazardly arranged. So human mind, human visual cognitive system is remarkable at this parallel processing. But if you want to do that with a machine and with classical techniques, you will be like this old crow who will put stones one by one and wait for a long time when the water comes to the mouth of this jar. The modern crow will use a straw like this and suck up the water. Deep learning, the entire modern machine learning is like this straw, which is not a science fiction, but uh, which is an engineered technology, very carefully engineered technology to assist the human beings. So what does deep learning offer? In traditional machine learning, you see the last 40 years question, central question in natural language processing, in speech processing, in computer vision, in image processing, everywhere, the central question was how to most optimally represent an image or a text signal or uh, uh, an image or a speech signal or a text document, etc., in terms of the most abstract and higher level features. So from that quest, huge amount of human intervened feature extraction techniques originate. So you have an input image or you have a piece of data, there is a human scientist who will extract the most optimal features from the lowest level features, who will combine the pixels of the image in suitable linear or nonlinear uh, weighted sum approach, and get to some abstract higher level features. These abstract higher level features will then be fed into a machine learning system, and the machine learning system will take the decision about the class. But deep learning eliminates the need for this human feature extraction. In deep learning, we have a huge feed-forward network which will take care of this feature extraction and classification simultaneously. Now, there are two types of deep inference models. One is predictive model or discriminative model, whose main example is convolutional neural network. The other one is called generative model. This is where we are going actually. The generative model, so this is the difference. The discriminative or predictive model is very happy to learn this Lakshman Rekha, this decision boundary between the two classes. So based on whether the new test point, whether the unseen data point is on the left or on the right of this line, it will decide about its class. But the generative models, classification comes for them as a secondary thing. What they try to do is they try to estimate the underlying spatial probability distribution from which the points from these two classes might have been sampled. This is very interesting. So, and this is a very classical problem in statistics, which usually faces huge difficulty in face of high dimensional data like the images. So the problem is, suppose I give you 10 numbers, scalar numbers, -3, +4.2, -6.8, and so on. And I tell you, estimate the Gaussian density, the Gaussian probability density function, the normal PDF, the mu and sigma of the Gaussian distribution from which these numbers might have been sampled. And of course, you will come up with methods like maximum likelihood estimation, maximum a posteriori estimation, and so on. But if instead of 10 numbers, if I give you 60,000 images and each image is, let's say, 100 by 100, 100 pixel by 100 pixel, which is nothing nowadays. So 100 pixel by 100 pixel means each image contains 10,000 lowest level features. Each image, if you flatten it, if you convert the image into a vector, it's a vector of 10,000 numbers. So you are going to work with 60,000 vectors, each having 10,000 dimensions, 60,000 arrays, each having 10,000 fields. So in that case, classical statistical methods will all fail, and only we will have to look for neural networks. Thereby comes the deep generative models. They try to estimate this underlying distribution. Why? Because if they can estimate it, then they can also sample from that distribution. So to a normal person, everything comes from nature or God, etc. But to a statistician or probabilist, everything is a sample from an underlying stochastic process. So if somehow we get to know the laws governing that stochastic process, the probability distribution underlying that stochastic process, then we would be able to sample from that process, right? So that's where deep generative models are coming. So I would skip some of this and directly go into it. So, by the way, the big breakthrough in predictive learning came with the deep convolutional neural networks from this particular paper published in Neurips 2012. This paper first put the industrial level deep convolutional network called AlexNet after the first name of this first author. And then actually after this paper, all the leading industries like Google, Facebook, Amazon, they started to invest lots of dollars and pounds behind development of deep neural network and deep machine learning research teams, as a result of which in 2015 came residual network with 152 hidden layers. These are huge neural networks with hidden layers, and the field developed like anything. So what happens in a convolutional net is something like this. This is important to understand the basic idea of GAN. I don't have much time, so I will go there very quickly. So in a convolutional neural net, what happens is you give an image as an input. This image passes through a lot of transformations through repeated application of convolutional filtering, which is much like dragging such a 5x5 or 3x3 filter over the image in order to identify the abstract and higher level features. followed by max pooling or downsampling. Pooling is a downsampling operation. So if even if you don't know or don't understand the entire flow, just take this with you, that the input is an image. From the image, through a sequence of convolution max pool operations and use of ReLU-like nonlinearity, rectified linear unit is a special nonlinearity, use of this, finally a vector is created. That vector contains the vector summarizes the most important and higher level features from the image. And that vector, so from a 100 cross 100 image, you may boil it down to a 50 dimensional vector, only 50 numbers. These 50 numbers will actually summarize the most intriguing features of the image. And then this vector will be used for, in a fully connected neural network, to predict the class of the image. The most interesting thing is, at the output from the same loss function, from the same loss, by taking derivative of the same loss, the convolutional filter parameters are also tuned or adjusted, so that this neural network may learn the context aware features. What features are most important for this particular context of the classification, which of course is determined at the final output. So in that context aware manner, the neural network is able to extract the features. What does that mean? So I am the same person or you are the same person, but at different contexts, different abstract features will be more important for you. If you go to a bank for a loan, in that case, your CIBIL score, your income, your monthly salary, all these things will be very important. If you go to a blood bank to donate the blood, in that case, whether you have thalassemia, what is your age, whether you have blood sugar, these things will be very important, not your bank balance. So the same person goes to two different contexts, different numbers start specifying the person. Here also. So based on the context, whether it's a bird or a non-bird, in that case, the most important features will become presence of feather, color, beak, etc. Whether it's a car or a non-car, presence of engine pipe, handle, wheel, these will become very important. So ConvNet can do this context-aware feature extraction. If you reverse the flow, so in a nutshell, before the final classifier layers, your input is an image and your output is a much lower dimensional vector specifying that image. If you reverse the flow of this ConvNet, your input is a vector and your output is an image. This is called deconvolutional neural net, and which will be a very important form of the generative adversarial networks. It's a 2014 breakthrough, very young. So when GANs were trained, so with medieval period portrait artists, charcoal portraits. So GAN, after some rounds of such training, so what is the crux of generative adversarial network? If you show it a number of images of some specific kind, it can actually try to estimate the underlying probability distribution of such images. And if it, in a non-parametric way, if it can do that even approximately, then this network can actually sample from those distributions. Sampling from the distribution means it can create artificial but very realistic images, text documents, speech signals, even nowadays music, whatnot. Okay, so it can create a lot of fake artifacts, some of which may have very important serious applications as well. So as I said, so when GAN was being shown with portrait artists' portraits, medieval period portrait artists, it created this at its own, and it was to be auctioned in USA for US dollar 4,32,500. Here, where there should be a signature of the artist, it's the GAN's objective function. So how does GAN work? I will just simply go there. So GAN comprises of two neural networks. One is called generator and the other one is called discriminator. The input to the generator is basically some kind of, so this generator is a deconvolutional network. What did I say just 2-3 slides back? In a deconvolutional network, your input is basically What is your input? Your input is, uh, just one moment. Yeah, your input is a vector. So in and your output is an image. So for the generator, the input is a vector comprising of random noise. It's called a code book vector. It's just a vector of some random numbers and very small in dimension, maybe 50, 100. And your output are basically some images generated from those noise vectors through the operations of inverse convolution and all. Okay. On the other hand, on the other hand, so the generator generates lots of such artificial images. But the generator doesn't have access to the real life example images or training images. On the other hand, the discriminator is like a two-class classifier. It's a neural network whose input is an image and whose output is a real score function. If the discriminator has access to the external training images, example images, the generator generated images also go into the input of the discriminator. The discriminator is like a teacher who will examine the outcome from the generator and put a score on it. If the discriminator thinks the input images are good enough, very realistic, then it will put a score close to 1. Otherwise, it will put a score close to 0 if it feels that the input images are not realistic enough. So the discriminator has a provision to compare between the actual real images and the generator generated images. So the generator is like this. You provide code vectors into it and it creates images. So, and the discriminator tries to provide a, criticism on that image in terms of a score. And as a result, the generator tries to drag the image more closely to the original generated image. On the other hand, if this is the function of a neural network generator. If it is a neural network classifier, then you provide an image and it tries to map the image into one of the possible class levels. So these two are very different. Discriminator, on the other hand, it takes the image as input and provides a score. If the image is good, like a true henshai face, it gives a high score, otherwise it will give a low score. Okay. Usually we employ the discriminator output or score to generate better quality images. So the general algorithm is for discriminator training is given a set of positive examples, randomly generate a set of negative examples, where from the positive examples are the actual real world images that come from the training set. Negative examples are those examples which are generated by the generator. The generator initially is completely untrained, so it will generate very poor quality images, as you can see from here. The discriminator learns to distinguish between these two, and usually these images are those which at the same time the generator is not trained yet, but these images are those which could still extract maximum score, although that score is very poor, but still maximum score from the current generator. Okay? So the generator creates an image. That image goes into the, now if the discriminator is properly trained, the generator created image goes into the discriminator. The discriminator provides it a very poor score. Based on the score, the generator weights are updated. The generator neural network is trained. That means its internal parameters are all tweaked through the same backpropagation algorithm, if you are familiar with it. Then the generator tries to improve its image until it extracts very good score from the discriminator, like 0.9. So the usual algorithm, soon after describing this algorithm, I will try to conclude. Am I audible to all of you still? Sometimes I need to ask it. Hello, can you hear me, all of you?
Yes, sir.
Okay, thank you. So maybe I will take another 5-6 minutes to conclude because it started some slightly late. So we initialize the generator and discriminator. That means we have two neural networks. We initialize their weights and bias values. In each training iteration, we sample some real objects. from a real world training set. Then the generator generates some fake objects like this. Then the discriminator is updated based on the manual labeling of the real, because as a user you know which one is real and which one is fake, so you can label them and you can update the discriminator. So as if the teacher goes to a teacher training camp outside your school or college and meets many other teachers from other schools, learns how they are teaching their students, and then the teacher comes back with a lot of experience. Now, the teacher is very critical to even the first boys of the class. So the generator generates images, and this new updated teacher, the discriminator, is giving them some score. Based on those scores, the generator updates. The generator tries its best to improve its image quality until it extracts very high score from the discriminator. Now this improved generator is used to create these negative images or fake images, so that at the next round the discriminator may be updated to learn even the finer levels of distinctions, even the subtle differences between the real and the fake images. Okay, and when the discriminator is updated, based on the updated discriminator, the generator is updated. We say in terms of game theory, these two neural networks are playing a two-player zero-sum game with each other, and its value function is quite mathematical. I will share the PPTs with the coordinators of this program. If you wish, you can look at the mathematical parts in detail. So this is the value function, which is written in terms of the expectation operator. But I think instead of looking at the value functions, etc., at this stage, it's better to look at some results that we may immediately show to you. Let me just give me 1 minute. So if you look at this simulation, this is exactly how GAN is. This is a handwritten GAN in Python. Handwritten means written for a small purpose, and you can see how it is generating the MNIST dataset images, how it is generating these images starting from very hazy patterns. How is it generating the MNIST dataset images here? And so with epoch, with number of epoches or number of iterations proceeding, its capability of generating such images is also improving. So when GAN was, shown with images of horses, churches, sofa sets, cycles, etc., GAN could generate all these images. As you can see, these are all generated by GAN from different classes. So these cycles, these sofa sets, these horses, these are all generated by GAN. None of them exist. And this is how the GAN images evolved with time. So from 2014, when we didn't have the luxury of using big GPU structures, so from then, as time proceeded, now you see this woman, you can see her wrinkles, her gray hairs, all the minute details, but do you believe that this woman doesn't exist on Earth? This camera clicked image, which looks so real, is actually of a person who is ghost, who doesn't exist. Similarly, not only human faces, GAN, the recent Big GAN project from Google DeepMind, it can generate lots of images from various classes of ImageNet. ImageNet is a huge data set of so many different types of images, like pasta, waterfalls, spaceship, coffee cup, and so on. You can see a new GAN is coming, almost GAN architecture for various purposes. Initially, it started in a big way for images, then videos, now text, even intra and inter-domain transfer, transferring the style of one image into the other, transferring the vocal style of one person onto the other, all these things, and cross-domain transfer from image to text, text to video, all these transferring, style transferring things are happening. This is just one This is from actually from this paper all the style transfer things begin. And if you look at this paper was published just about 4 years back in 2017 December, I think, the famous ICCV conference. So you can see if you provide this sort of a hand-drawn picture by Claude Monet, it can convert it into a camera-clicked image. So if you click the picture of some space, and CycleGAN architecture is trained with, the brush strokes and canvases of famous artists like Claude Monet, Van Gogh, Cézanne. So CycleGAN could import the style of Vincent van Gogh into your photograph. It can show you how that scene would look like if Vincent van Gogh would have painted it on a canvas. Similarly, it could convert the horse into a zebra and zebra into horse. This is just a nice illustration. So from there, this style transfer thing started, which almost uh, revolutionized the videography, special effect, computer vision, special effects, social media. You can very easily annotate, you can very easily create a content, multimedia content, sitting in your home and just with one handheld devices. You could take some video snapshots, you can nicely edit them, you can convert, you have so many filtering options, all of them, most of the filtering options industrial on smartphones and androids, iPhones used these days actually have these GAN based tools at their back end. Okay, so this is the neural photo editor. You can see how you can, it's a behavioral photo editor. You can put this cursor at some place and it shows how the hairstyle looks like. Similarly, we have pix to pix. You provide this sort of an image and hand drawn image, and the output is an actual, but this building is not photographed, this is made actually. Similarly, black and white to color. I was showing some illustrations. This is labels to street scenes and vice versa. These are very, very important backends for self-driving cars also. They have very serious applications in rendering of climate informatics related images, terrestrial, astronomical images, down to geosciences analysis and this sort of self-driving cars and where not. So these are some of the very, very important applications of improved GAN architecture. This is just another nice application. You can see you can import the expression of any person onto any other person. Like you can import your own expression onto how Mona Lisa would look like if she imitates your expressions. But besides that, they have very serious applications as well. As you may see, this generation of artificial stuff or artificial, style transfer. I mean, now it's very easy to, transfer the vocal style of some very iconic person. Obviously, the most famous person will be chosen for that. For example, uh, Mr. Amitabh Bachchan's baritone voice, that vocal toning could be transferred onto me. So as if this lecture is given, the same deep learning content is being spoken by Mr. Bachchan, which is very easy to do nowadays with little bit of programming. So there are lots of opportunities in this particular area, and many things to be done. I would actually stop here because I think the time is flowing out. If you have any questions, I would be happy to answer at this moment. I think I was given a time up to 1:20, but anyway, it started slightly late, so I already overshot by 13 minutes. Now, if you have any other questions or discussions or comments, I would be happy to participate. Hello, am I audible?
Yes, sir, you are audible. Uh, so, sir, can we allow some of the questions from the participant? Hello, sir, am I audible?
I mean, you are audible to me. I can hear you.
Yeah. So, students, if you have any query, I think you can directly ask to our sir. Uh, you can unmute and ask if you have any question. I think, sir, We are not getting any questions from the. So actually, so I think, sir, most of the students are first year, so they might
Yeah.
not be that much gone in depth with this machine learning topic. But anyway, so we have this recording with us, and we'll also have we have the YouTube streaming, so people can post their queries there also. Anyway, so over to you, ma'am. Over to you, Jyoti, ma'am. We can thank you, sir.
Okay, thank you
Yeah,
so
thank
much,
you, sir.
sir, for your engaging talk. And from Haldia Institute of Technology and from the School of Applied Science and Humanities, we extend our heartfelt thanks to you for sparing some time from your very busy schedule, sir. Thank you so much
Thank you.
once again for being here with us today, sir. Have a
Thank
good day.
you.
Thank you.